Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. To distinguish the electromotive force, or EMF, and potential difference, or PD. Electromotive force is defined as the work done, or energy transferred, per unit charge of the power supply that driving charge around a complete circuit. Potential difference is defined as the work done, or energy transferred, per unit charge that passing charge through a component. The electromotive force is the other forms of energy such as chemical energy in batteries, or kinetic energy in generator, to transfer into the electrical energy. The potential difference is the electrical energy to transfer into the other forms of energy. The formula for the electromotive force can be written as E equals W divided by Q, where E is EMF in volt, W is the work done or energy transferred in joule, and Q is the charge in coulombs. The formula for the potential difference can be written as V equals W divided by Q, where V is PD in volt, W is the work done or energy transferred in joule, and Q is the charge in coulombs. The EMF and PD are measured in volt, and 1 volt is equivalent to 1 joule per coulomb. The internal resistance of the power supply. The internal resistance caused by the material in the power supply. For example, in a battery or cell, the internal resistance is due to the resistance of the electrolytic solution in the cell. In a generator or transformer, the internal resistance is due to the resistance of the coils and other wiring in the apparatus. The internal resistance is what makes batteries and cells warm up when they are used. Consider a battery of EMF E and internal resistance R, to connect in series with the external resistance R and switch S, as shown. The voltmeter V1 measures the EMF E, or terminal PD of the battery. The voltmeter V2 measures the PD across the external resistance R. As the switch S is opened, as shown, no current flows through the battery, so no heat energy is lost due to the internal resistance, and there is no lost voltage. The voltmeter V1 is now equal to the EMF E of the battery. The voltmeter V2 is 0, because no current flows through the circuit. As the switch S is closed, as shown, the current, I, flows through the battery, so heat energy is lost due to the internal resistance, and there is a lost voltage. The voltmeter V1 is decreased to less than the EMF E. The voltmeter V2 is equal terminal PD that measured by V1, so V2 equals V1. As the resistance R decreases, the current I increases. This causes the lost voltage at the internal resistance R to increase, resulting in a decrease in the terminal PD of the power supply. According to the conservation of energy, we can write the equation as the EMF E equals PD across the external resistance plus PD across the internal resistance. The EMF E of a battery represents the work done per unit charge to move charges around a circuit. This work done is equal to the sum of the energy transferred per unit charge across the external resistance, which is the voltage across the external resistance R, and the energy transferred per unit charge across the internal resistance, which is the voltage across the internal resistance. The voltage across the external resistance R is measured by the voltmeter, which is equal to the terminal PD of the battery. We substitute the voltage across the external resistance R equals V, and the voltage across the internal resistance equals I times R. And V equals I times the external resistance R. Then we factor out I, like this, where I is the current that flows through the circuit. the experiment to determine the internal resistance of the battery. We set up the circuit, as shown in the diagram. By varying the external resistance R, we recorded the current I from the ammeter, and the terminal PD from the voltmeter in the table. We plotted the graph of the PdV against the current I, as shown. The graph is the straight line with negative gradient, as shown. From the equation of the EMF, E equals V plus IR. We rearrange the equation, as V equals E minus IR. And V equals negative RI plus E. From the equation of the straight line, Y equals mx plus C. Y-axis is represented the terminal PdV. X-axis is represented the current I. So, the gradient M equals negative internal resistance R. And the y-interception C equals the EMF E. So, we can calculate the internal resistance of the power supply using the gradient of the graph. The dissipated power at the external resistance R. From the previous experiment, by varying the external resistance R, we recorded the current I from the ammeter, and the terminal PD, V, from the voltmeter in the table. We calculated the power dissipated in the external resistance R using P equals I squared R, and recorded the results in the table. We plotted the graph of the dissipated power P against the external resistance R as shown. The power output from a source is dependent on the internal resistance of the source, and on the external resistance R. The graph shows how the power output varies. We see that there is maximum power output when the external resistance is equal to the internal resistance. So, the maximum power P dissipated at the external resistance R, when the external resistance is equal to the internal resistance. The shape of this graph corresponds to the theoretical curve of the equation P equals E squared R divided by sum of external resistance and internal resistance squared, where EMF E and internal resistance are constant. This equation can derive from P equals I squared R. As EMF E equals terminal PD V plus the current I times the internal resistance R. We rearrange the equation, as I equals E divided by sum of external resistance and internal resistance. Substituting this equation into this equation, like this. We get the P equals E squared R divided by sum of external resistance and internal resistance, like this. Exam style question 1. A cell of internal resistance R and electromotive force, EMF, E is connected in series with a resistor of resistance R. The resistance R and the EMF E remain fixed. The internal resistance R of the cell changes over time. Which graph best shows the variation of the current I in the circuit with the internal resistance R? From the equation EMF E equals the current I times external resistance plus the current I times internal resistance. We factor out I, like this. And then rearrange the equation, I equals E divided by sum of external resistance plus internal resistance, like this. Where EMF E and the external resistance are constant. So, the theoretical curve of this equation for the current I against the internal resistance is the reciprocal graph. This graph has the asymptotes at R equals negative, R and I equals 0. The y-interception at I equals E over R, like this. So, B is correct. Exam style question 2. A cell with internal resistance is connected to a variable resistor, R as shown. The resistance of R is gradually decreased. How do the current I and the terminal potential difference across the cell change? As the external resistance R decreases, causing the current I to increase. So, A and B are incorrect and C and D are correct. From the equation the EMF E equals V plus I times R. V is the terminal PdV across the cell. As the current I increase, causing the IR to increase. This causes the terminal PdV to decrease. So, C is correct. Exam style question 3. A cell is connected to a resistor of resistance 3.00 ohms. The current in the resistor is 1.0 amperes. A second identical resistor is added in parallel. The current becomes 1.93 amperes. What are the EMF E and internal resistance R of the cell? From the equation, the EMF E equals the current I times the external resistance R plus the current I times the internal resistance R. For first circuit, we substitute the current I equals 1 amperes, and the external resistance R equals 3 ohms. So, E equals 3.00 plus the internal resistance R. For second circuit, we calculate the total resistance using 1 over RT equals 1 over 3 plus 1 over 3. So, total resistance RT equals 1.5 ohms. We substitute the current I equals 1.93 amperes, and the external resistance R equals 1.5 ohms. So, E equals 2.895 plus 1.93 R. We solve two simultaneous equations to find the internal resistance R like this. We get the internal resistance equals 0.113 ohms for three significant figures. We substitute the internal resistance into this equation. We get the EMF E equals 3.11 volts for three significant figures. So, C is correct. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Kirchhoff's first law. The sum of the currents entering any junction, in an electric circuit, is equal to the sum of the currents leaving that junction. This is a restatement of the law of conservation of charge. It means that the current going into a point is equal to the current leaving that point. Work example 1. State the relationship of the currents in the diagram. The sum of the currents entering a point A is equal to the sum of the currents leaving a point A. We see that the currents I2 and I3 are entering the point A, and the currents I1 and I4 are leaving the point A. So, we get the I2 plus I3 equals I1 plus I4. Kirchhoff's second law. In any closed loop in an electric circuit, the algebraic sum of the electromotive forces is equal to the algebraic sum of the potential differences. This is restatement of the law of conservation of energy. Remember that potential difference between 2 points is the work done per unit charge in moving from one point to the other. If the start point and the end point are the same, then the net energy change, or work done, must be zero. Exam style question 1. Two cells of EMF E1 and E2 and negligible internal resistance as shown. Use Kirchhoff's laws to state the relation A between currents I1, I2 and I3. Using the Kirchhoff's first law for this relationship. At the point B, the sum of the currents entering is equal to the sum of the currents leaving. We see that the currents I1 and I2 are entering the point B, and the current I3 is leaving the point B. So, I1 plus I2 equals I3. B between E2, R, I2 and I3 in loop BCXYB. Using the Kirchhoff's second law for this relationship. So, the sum of EMF is equal to the sum of PD in loop BCXYB. The EMF E2 drives a current flow from positive to negative in a clockwise direction. The current I3 flows through this resistor R in clockwise, the same clockwise direction as the current driven by E2. So I3 is positive. So, the PD across this resistor is I3R. The current I2 flows through this resistor are in the same clockwise direction as the current driven by E2, so I2 is positive. So, the PD across this resistor is I2R. So, E2 equals I3R plus I2R. See, between E1, E2, R, I1 and I2 in loop ABCXYZA. Using the Kirchhoff's second law for this relationship. So, the sum of EMF is equal to the sum of PD in loop ABCXYZA. The EMF E1 drives a current flow from positive to negative in an anticlockwise direction. We give the current to flow in anticlockwise direction is positive. So, E1 is positive sign. The EMF E2 drives a current flow from positive to negative in a clockwise direction. So, E2 is negative sign. The current I1 flows through this resistor are in anticlockwise, so I1 is positive. So, the PD across this resistor is I1R. The current I2 flows through this resistor are in clockwise, so I2 is negative. So, the PD across this resistor is minus I2R. The current I1 flows through this resistor are in anticlockwise, so I1 is positive. So, the PD across this resistor is I1R. So, E1 minus E2 equals I1 minus I2R plus I1R. We simplify the equation as E1 minus E2 equals 2I1 minus I2R. Resistance in parallel circuits. The cell with EMF E and 3 resistors are connected in parallel circuit, as shown. To find the total resistance of resistors connected in parallel, we can use Kirchhoff's laws. We can see the same potential difference across each resistor, equal to EMF E, because it is a parallel circuit. So, E equals V1 equals V2 equals V3. Using Kirchhoff's second law. So, the sum of EMF is equal to the sum of PD. For the green loop, the EMF E equals PD across R1, which is V1, and V1 equals I1 R1. So, I1 equals E over R1. For the pink loop, the EMF E equals PD across R1, which is V2, and V2 equals I2 R2. So, I2 equals E over R2. For the blue loop, the EMF E equals PD across R3, which is V3, and V3 equals I3 R3. So, I3 equals E over R3. And the current I from the cell is equal to E over total resistance. Using Kirchhoff's first law, the sum of the currents entering a junction A is equal to the currents leaving a junction A. So, I equals I1 plus I2 plus I3. Substituting I equals E over total resistance, I1 equals E over R1, I2 equals E over R2, and I3 equals E over R3. We cancel out E, like this. So, 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Resistance in series circuits. The cell with EMF E and 3 resistors are connected in series circuit, as shown. The EMF E drives a current I flow through a circuit, and passing through each resistor. To find the total resistance of resistors connected in series, we can use Kirchhoff's second law. The sum of EMF is equal to the sum of PD around a circuit. The PD across R1 equals IR1. The PD across R2 equals IR2. The PD across R3 equals IR3. So, E equals IR1 plus IR2 plus IR3. We factor out the current I, like this. So, E over I equals R1 plus R2 plus R3. Substituting E over I equals total resistance, like this. So, total resistance equals R1 plus R2 plus R3. Worked example 2. The diagram shows a network of resistors made up of 5 identical resistors, each of resistance R, calculate the total resistance of the network. The total resistance of the top line is R plus R equals 2R. The total resistance of the pair of resistors in parallel can be calculated using 1 over total resistance equals 1 over R plus 1 over R, resulting in 2 over R. So, total resistance in parallel equals 0.5 R. The total resistance of the lower line is 0.5 R plus R equals 1.5 R. So, the total resistance of the network AB is 1 over total resistance equals 1 over 2 R plus 1 over 1.5 R equals 7 over 6 R. So, total resistance equals 6 R over 7, or equals 0.86 R for two significant figures. Hey everyone, welcome to PLA Academy. Hope you found this video useful. If you did, it'd be awesome if you could subscribe, like the video, share it with your friends, and maybe drop a comment. Your support really helps me make more videos. In this video, I covered everything on the syllabus, like you can see in the figure. Potential divider circuit. A potential divider circuit consists of components connected in series, and the potential difference is divided across each component. The circuit of the potential divider is shown. Two resistors are connected in series. The EMF V input of the power supply is shared between them. So, V input equals V1 across R1 plus V2 across R2. The current remains the same any points in series circuit. So, the current I from power supply equals I1 passing through R1 equals I2 passing through R2. Therefore, the PDV across each component is directly proportional to its resistance R, since the current I remains constant. From the equation, V1 equals IR1 and V2 equals IR2. We divide the both equations together, like this. We cancel out I, like this. So, the ratio V1 to V2 equals R1 to R2. An useful alternative formula as V input equals I times total resistance. Substituting total resistance equals R1 plus R2. So, the current I equals V input over sum of R1 and R2. The PD across R1, V1 equals I times R1. Substituting I equals V input over R1 plus R2. So, V1 equals R1 over R1 plus R2 times V input. The PD across R2, V2 equals I times R2. Substituting I equals V input over R1 plus R2. So, V2 equals R2 over R1 plus R2 times V input. Resistor R1 is replaced by a thermistor. The thermistor resistance decreases when the temperature increases, and vice versa. As the temperature increases, the thermistor's resistance decreases, causing Vt to decrease and increasing V2. As the temperature decreases, the thermistor's resistance increases, causing Vt to increase and decreasing V2. As R1 is replaced by a light-dependent resistor, LDR, the resistance of the LDR increases when it gets dark, and vice versa. As the light intensity increases, the LDR's resistance decreases, causing PD across LDR to decrease and increasing V2. As the light intensity decreases, the LDR's resistance increases, causing PD across LDR to increase and decreasing V2. Exam-style question 1. The circuit shown consists of two resistors of resistances, 10 kiloohms and 50 kiloohms, and a component Y. A 6.0 volts supply is provided. The electric potential of the bottom wire is 0 volts. The current in component Y is negligible. What is the electric potential at junction X? The current in component Y is negligible. This means the current equals 0. So, the PD across 50 kiloohms equals the PD across the component Y. We give this PD to be V2. The electric potential at junction X equals the voltage at X. We calculate the PD V2 using the equation V2 equals R2 over R1 plus R2 times V input. From the circuit diagram, R1 equals 10 kiloohms, R2 equals 50 kiloohms, and V input equals 6.0 volts. We substitute R1, R2 and V input into the equation of V2, like this. We cancel out K, which represent kilo, like this. We get V2 equals 5.0 volts. We give this point as A, voltage at A equals 0. The PD V2 across R2 equals voltage at X minus voltage at A. And the voltage at X equals V2 plus VA equals 5.0 plus 0 is equal to 5.0 volts. So, D is correct. The potentiometer is shown. A potentiometer is basically a potential divider, with a variable resistor to give variable voltage output. A uniform conductor rod, same cross-sectional area and material throughout, of length L, with a sliding contact, is divided into two segments, as L1 and L2. According to the resistance, is directly proportional to length. A voltmeter is connected across the different lengths of the rod, the PD would be proportional to the length. Therefore, a larger segment of rod's length will exhibit a greater PD. So, the V output equals R1 over R1 plus R2 times V input. We give the resistance R1 is proportional to L1, so R1 is equivalent to L1. The resistance R2 is proportional to L2, so R2 is equivalent to L2. So, we can deduce that V output equals L1 over L1 plus L2 times V input. Substituting L1 plus L2 equals L. Therefore, V output equals L1 over L times V input. Exam style question 2. In the circuit shown, a potentiometer of total resistance 120 ohms is connected in parallel with a resistor of resistance 150 ohms and a resistor of resistance R. The battery has electromotive force, EMF, 12 volts and negligible internal resistance. The voltmeter reads 0 volts when the slider of the potentiometer is 1/4 of the way from its lower end as shown. What is resistance R? The voltmeter reads 0 volt. This means that the PD across lower end equals the PD across the resistance R over R. We can calculate the PD across the lower end using V output equals L1 over L times V input. From the circuit diagram, V input equals 12 volts, L1 equals 1/4 L, and the upper end equals 3/4 of L. Substituting V input and L1 into this equation, like this, we get the V output equals 3 ohms. So, VR is also equal 3 ohms. We can calculate the resistance R using V2 equals R2 over R1 plus R2 times V input. Substituting V2 equals VR equals 3, R1 equals 150, R2 equals R, and V input equals 12. We solve the resistance R equals 50 ohms. So, C is correct. Using a potentiometer to compare potential differences. The potentiometer is shown. This circuit can be used to compare the EMF of two cells. The position of the sliding contact is adjusted until the current through the galvanometer is 0. The EMF, E2, is now equal to the potential difference V across the length L of the resistance wire. This method of measurement is known as a null method. So, the PDV equals L over L0 times E1. Substituting V equals E2, like this. We rearrange the equation, as the ratio of E2 to E1 equals the ratio of L over L0. Exam-style question 3. A power supply and a solar cell are compared using the potentiometer circuit shown. The potentiometer wire PQ is 100.0 centimeters long and has a resistance of 5.00 ohms. The power supply has an EMF of 2.000 volts, and the solar cell has an EMF of 5.00 millivolts. Which resistance R must be used so that the galvanometer reads 0 when PS equals 40.0 centimeters? The galvanometer reads 0, this means that the EMF of solar cell equals the PDV across PS. So, the PDV across PS equals 5.00 millivolts. We can be calculated the PD across PQ using the equation V1 over V2 equals R1 over R2. According to the resistance is proportional to length. So, we get V1 over V2 equals L1 over L2. Substituting V1 equals V across PQ, V2 equals V across PS equals 5 times 10 power negative 3 volts, L1 equals 100 centimeters, and L2 equals 40 centimeters. We solve the V across PQ equals 0.0125 volts. So, we can calculate the PD across R equals 2 minus 0.0125, which is 1.9875 volts. We give the current I to flow from the power supply with EMF 2 volts, and then passing through wire PQ and the resistor R. We can calculate the current I using VPQ equals IRPQ. Substituting VPQ equals PD across PQ equals 0.0125 volts, and RPQ equals resistance of wire PQ equals 5 ohms. We solve the current I equals 0.0025 amperes. We can calculate the resistance R using the equation VR equals IR. Substituting VR equals 1.9875 volts, and I equals 0.0025 amperes. We solve the resistance R using equals 795 ohms. The potentiometer used to compare the resistors is shown. This series circuit of the resistors R1 and R2 is then connected to the potentiometer, as in the diagram. The position of the sliding contact is adjusted until the current through the galvanometer is 0. So, the PD, V1, across R1 is equal to the PD across L1, and the PD, V2, across R2 is equal to the PD across L2. So, the ratio of PDV across L1 to the PDV across L1 equals the ratio of L1 to L2. And the ratio of V1 to V2 equals the ratio of L1 to L2. The current I flows through the whole series circuit. The PD V1 across the resistance R1, which is V1 equals I times R1. And the PD V2 across the resistance R2, which is V2 equals I times R2. Substituting V1 and V2 into this equation, like this. We cancel out I, like this. So, the ratio of R1 to R2 equals the ratio of L1 to L2. Exam-style question 4. Potential differences across two resistors of resistances R1 and R2 are compared using a potentiometer wire, uniform resistance wire, in the electrical circuit shown. One terminal of a galvanometer is connected to point X. The galvanometer reads 0 when its other terminal is connected to a point that is a distance of 60 centimeters from one end of the potentiometer wire. One terminal of a second galvanometer is connected to point Y. This galvanometer reads 0 when its other terminal is connected to a point that is a distance of 80 centimeters from the same end of the potentiometer wire. What is the ratio R2 to R1? The two galvanometers read 0, this means that the PD V1 across R1 equals the PD across L1, and the PD V2 across R2 equals the PD across L2. We calculate the ratio of R2 to R1 using R2 over R1 equals L2 over L1. From the diagram, L1 equals 60 centimeters, and L2 equals 80, minus 60 is equal to 20 centimeters. Substituting L1 and L2 into this equation, like this, we get the ratio of R2 to R1 equals 1 to 3. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.